Thank you, Zach. All right, so my name is Bridget Guildner. I'm a master's student at University of Montana, working with Dr. Solomon Dabrowski, and I'm in the systems ecology program there. And today I'm going to be talking about some of my work using fine-scale, process-based climate and hydrologic inputs to drive species distribution hindcasts at the last glacial maximum and at the mid-Holocene 6,000 years ago. So we know the climate's changing, and we've heard a lot of different projections for how species are going to respond to these changes. And so, for example, here we have a projection of mountain hemlock distributions, current versus 2060, from the Moscow Forest Sciences Laboratory, and showing the sharp contraction in their range as climate changes and warms and becomes a little wetter. So one question we might have, whoops, apologies. Oops. There we go. So when we're looking at these projections, one question we might ask is, what is an appropriate scale to be analyzing these distributions at? Because some of these species might be able to persist in smaller areas than the grid cells that we're modeling them at. These large grid cells also may not capture fine scale processes like cold air pooling, where the local climate becomes decoupled from regional climate. And so if we model all of these at broad scales, we might miss some of those dynamics. And these could be really important for these species responses, because if they only have to move a short distance to reach a hospitable climate that's nearby, but in maybe a local microclimate, they might be able to persist in these areas that they otherwise might not have been able to if it was just dominated by the regional climate. So I'm going to be looking at this Clearwater Refugium, which is an area in and around the Nez Perce Clearwater National Forest, there in red. And so this area, we have a lot of evidence from University of Illinois researchers, University of Oregon researchers, and University of Idaho, showing that there are a number of herbaceous and amphibious species that were isolated in this region from the phylogeographic evidence. And so this raises questions about this refugium and what kind of tree species might have grown there. So what we wanted to do was look at this inland wet belt disjunct distribution of mountain hemlock and western red cedar there in the dark and lighter green. And as you can see at the bottom of the Cordilleran ice sheet 21,000 years ago, there was this area that coincides with their current distribution that might have been able to shelter them in place if the local climate was hospitable. So there's this open biogeographic question about whether these species persisted in this area or migrated over from the Pacific coast. And we wanted to be able to put some bounds on whether this was a plausible thing from the climatic perspective. And we wanted to look at the impact of using finer scale temperature inputs and mechanistic water balance inputs to take a look at whether these species might have been able to live there. All right. So to address that question, we use these downscaled climate models from the Paleoclimate Modeling Intercomparison Project. And basically what those are is it's just the CMIP models, a selection of the CMIP models, run back with forcings from 21,000 and 6,000 years ago. So at the last glacial maximum and the mid-Holocene. We downscaled those using TOPO-WX temperature surfaces from Jared Euler at the University of Montana, using PRISM dew point and precipitation, and reanalysis data for wind and radiation. We also used a much finer scale process-based temperature model from the US Forest Service, from Zach Holden, to examine whether using an even finer scale with more mechanistic inputs impacted the kinds of projections we could make. And instead of using just simple precipitation, we wanted to use a mechanistic water balance model that would reflect the actual availability for these species in these places at those times, not just precipitation, but what water would be available for them. And then finally, we fit species distribution models to those using forest inventory analysis plot data and current norms. We also looked at the warmest and wettest scenarios and the coldest, driest scenarios to put some plausibility bounds on that. And we used boosted regression T models to fit those distribution models. So I want to go into a little more detail on this water balance model. It's essentially a mass balance bucket model where we take the incoming precipitation in the form of snow or rain determined by the temperature, and we basically tally that on a monthly time step and partition that water into evaporative demand, evapotranspirative demand, I should say, runoff, and storage in the soil or in snowpack. And so the advantage of this model is that, as we were hearing in the plenary session yesterday, the timing and phase of water is critically important in understanding what is actually available for plants on the ground where they're living. Just looking at precipitation might not capture some of the demand, might not capture snowpack, might not capture melt dynamics. So the way this basically works is we used a StatsGo soil capacity model to establish basically the size of our buckets, poured in our inputs, and then subtracted demand, and whatever's left gets partitioned into runoff or snowpack, depending on whether there's appropriate temperatures for that. So let's see. So first of all, I'm going to give you just a broad overview of the biogeography of these species at this time. So for mountain hemlock, we found that using the ensemble mean of those GCMs, that their distribution was primarily located in the Oregon Coast Range and Cascades, and a little bit down through Northern California and the Sierra Nevadas. And this is mostly responding to minimum temperatures in this mountain hemlock model. By the mid-Holocene, 6,000 years ago, we find that they've moved pretty far northward, all the way up into the North Cascades and into possibly the inland wet belt. And I should say that since we're extrapolating to a very different climate, it may be inappropriate to call these distribution models, so I'm going to call them climate suitability maps here, just to emphasize that we don't have evidence that these species were there, but these are areas where they could have been. So for mountain hemlock, and then for western red cedar, we find that they were located mostly in the Oregon Coast Range and Willamette Valley, or could have been located there, and the North California into the Sierra Nevadas again. And that by the mid-Holocene, they've moved substantially northward up into the Olympic Peninsula, the Oregon Cascades, and some distribution in that inland wet belt. So just for a general sense of how these species are responding. But now I want to zoom in on the finer scale outputs that we have. So on the left there, we have the 800 meter resolution projections that we made. And as you can see, there's some areas along the Idaho border where along these ridge tops we think they might have been able to grow. But when we zoom in and use this fine scale process model at 250 meters, all of a sudden a lot of these ridge tops really pop out as potential climate. And so these are areas where we might not catch this at a broad grid cell scale, but if we are able to use a much finer process-based model, it's possible that we would see different projections for these species, that there might have been these little microrefugia that they could have persisted in, even though the regional climate at the broader grid cell scale does not indicate that. So, and for western red cedar, we see something similar. In this case, they're not responding to the minimum temperatures and ending up on ridge tops, but instead we're finding them down in the valley bottoms. And you can see that this fine scale process model really captures the water availability in those areas. So this is a really nice example of why it might be important to use this water balance instead of just precipitation, because it captures the water availability down in those valley bottoms as well. It gives us a better idea of the spatial patterning of these potential habitats as well. So, and then since we wanted to put some bounds on the plausibility of these things, we're combining these models with other lines of evidence, of course. We wanted to see what would have been possible with the coldest and driest scenario, so the 5th percentile coldest and driest, versus the warmest and wettest scenarios predicted by those GCMs. So on the left there, we have the coldest and driest, and you can see that while there's not a lot of area for these species to have been able to grow, there are some areas up on those ridgetops that still pop out as potential habitat for these species. And so even in our most conservative estimates, we have some evidence that there would have been suitable habitat for these species, which we can then combine with other forms of evidence, like the fossil record, or palynology, or phylogeography. But by the warmest and wettest scenario, there appears to be a great deal of suitable climate for these species. And again, along those ridge tops is mostly where we find the mountain hemlock. They're responding mostly to minimum temperature. So, and then same difference with western red cedar. Basically, on the coldest and driest scenarios, we found that there was not a lot of suitable habitat for them. But if that distribution was skewed a little more toward the warmest and wettest side, there would have been a great deal of habitat for these species. So this emphasizes the importance of not just using the ensemble mean, but also looking at these bounds of plausibility for these species. and trying to determine whether it's possible that they would have lived there or not. So there's some limitations to this analysis, of course. We used FIA data, which does not extend up into Canada. So if anything, this is a more conservative prediction. We're not capturing the coldest and driest part of their range necessarily, or coldest and wettest, sorry. It also doesn't account for any environmental plasticity. If these species are responding differently now to climate than they were 21,000 years ago, that's not going to be captured by these models. So we're assuming that all of these tree species are going to respond the same as they would have. It also doesn't account for glaciers or lake effects, which is, we would love to include. We're still working on how to include that in these models. But that could potentially have a moderating effect if it's a glacial lake, or even an exacerbating effect in the case of glacial winds coming off. And then finally, we need other lines of evidence to be able to make actual conclusions about where these species lived and whether they were able to live in these glacial refugia. For example, we're using palynology pollen evidence from our collaborators at the University of Oregon. We're working on that, and so far that's been mostly consistent with these predictions. And we have researchers at the University of Illinois looking at the phylogeographic evidence for these species. So we're going to combine this to make some more robust conclusions about where these species actually would have lived and whether these refugial dynamics might have been something that could help answer that biogeographical question. So just in conclusion, these really emphasize the importance of considering scale and process when we look at species distribution models, and not just looking at simple temperature and precipitation. If we had just used temp and precip, we might have missed some of those valley bottom dynamics for western red cedar, and we wouldn't have had a very good idea of the timing and the storage availability for water. So this really helps us get a better idea of what's actually available for the plant at that time, not just at an annual scale. And finally, the water balance is so important with integrating all of that evaporative demand. As we saw, the effects of, in this last water year, the effect of having a low snowpack and high evaporative demand can be a really synergistic effect. And so the water balance model captures a lot of that in a way that using just precipitation might not. So I think that's all I have. Oops. So thank you very much for listening. Any questions?
Do we have 5 or 6 minutes for questions for Bridget? Anybody has any questions?
Yeah.
I was wondering, if you create a coarser climate-based model, that's completely independent of your resolution process-based model, or do you combine
Good question. We're treating them completely separately at this point. The temperature surfaces were derived in just a very different way. Oops. So it doesn't make sense to combine them as a mean or anything, but we are using the other inputs from the previous model. So we're keeping everything constant but the temperature surface in that case. Okay, if that helps. Good questions. All right. Cool.
No more questions for Bridget?
All right.
All right.
Cool.
Well, thanks again, Bridget.
Thank you.